record is somehow. Okay, the share screen is a bit strange. It's not showing my share screen. Anyway, I will just proceed. Right, so yes, you can look up proofs for this. I'm sure there's some online, but write up your own version, right? And then in terms of beta priors, so it might look scary because of the beta function and gamma function, but what this question essentially takes you through is essentially first by showing that the beta function is bounded, which is some elementary algebra that takes a little bit of thinking, and then we prove that the expression above is a valid probability distribution. Essentially, as you can see, the key here is realizing the beta function. It's a number of terms, and the big B function comma A comma B is essentially the normalizer of the terms after it, right? Furthermore, well, this proofs will require you to use the definition of gamma function that's written below, right? And the definition of gamma function is also given here. So you will basically work through the steps of proving that the beta is a well-behaved distribution. So what is question 2.3 asking us to do is essentially look at this recursive relationship of beta functions, right? Or A and B does not have to be integers, but one can derive the beta function A plus 1 comma B from the beta function of A comma B, which is nice. And you're going to try and do that, which goes back to the definition of beta function given gamma functions. And then, yeah, you can play with the integrals and hopefully it comes out fairly soon. And all this algebraic exercise in this big question, the second part of the question is preparing us for looking at coin flips, right? So what we do here is in the frequentist view, we think about coin flips as parameterized by the parameter theta. That is the probability of the coin come up heads, x equals 1. So what we want to show is that the prior, if we put a beta prior on theta, parameterized by A and B, we want to show that the posterior distribution of theta is also a beta distribution. And this is the definition of conjugate priors. Yeah, which is very handy analytically. So you might ask, oh, why do I want a beta prior? Right, why do I care about a beta prior? So a prior is a way to specify our essentially belief of the distribution without having seen any data yet. For example, our prior belief can be that the coin flip, right, there is non-zero probability for both heads and tails. And if we're going to, if we're doing maximum likelihood estimates, it's hard to specify conditions like this, because if we throw a coin and it comes up heads twice in a row, maximum likelihood estimates will not know what to do except saying, oh, it came up heads so far, and it's always, then it will always come up with heads, and that's not good, right? So we can also think about priors as a way of smoothing the estimate, right? And this particular expression here is a way to state that more precisely. It basically says if we have H heads and T tails so far, then the posterior probability is smoothed by the prior. Basically, the posterior after seeing that data is essentially A plus H versus B plus T, rather than just H versus T, which suffers from the problem of the estimates of 0, right? And then we then questions 3 and 4 are essentially helping us build more intuitions about the beta prior, right? So if we say that the prior is beta parameterized by A and B, we're essentially saying the expected mean of the distribution is essentially the equivalent of theta is A over A plus B. There's a variance. Moreover, you might say if in this case it's the ratio between A and B matters, why do we want two values of A and B? The value of that is basically in the expression above, where A plus H and B plus T essentially denotes the magnitude of smoothing, right? Imagine, let's say A and B equals 1, then we're saying we're unsure, but we're saying that if we have, say, 1,000 coin flips, then the A and B being 1 don't really matter. But if we're saying A and B equal to 1,000, then we are saying if we observe 10 coin flips, then the prior still dominates. We will see a similar expression like this in Bayesian linear regression on Friday, where essentially the relative of the prior and the data point comes into play when we estimate, say, a Bayesian version of the weights W. Right, so that's the motivation behind this assignment. Right, so question 5 and 6, or 5 is essentially doing the same thing as 3 and 4 here, except for the posterior. As we said, the posterior and prior has the same form, so it should be easy. It should be mechanical. And then question 6 asks you to plot the posterior probability. This helps build intuition. You can use SciPy. I believe the updated version of this PDF does have pointers to SciPy. If not, feel free to ask. It's also helpful to get familiar with the appropriate neighborhoods of NumPy and SciPy that are often used in this class, right? And this, like, some part of this assignment and the lab helps you do that. And then in question 7, we are essentially looking at the posterior of the parameter and looking at where, like, basically we're supposed to find a point where this particular interval contains at least 99% of probability mass. And exercise 4 extends this coin flip analysis by saying that we now maybe don't exactly observe the exact results of coin flip, right? So the diagram goes as follows. So we have parameter theta that drives the coin flip, and we can have priors on theta. And then afterwards, what we observe can be essentially a noisy version of the coin flip. And we are to derive what the noisy version looks like. You might ask, why do you care, right? So in fact, this particular picture, it's simple looking, but it drives modern communication, right? So digital communication communicates in 0 and 1, and it gets sent through, say, a wireless channel between the cell tower and our mobile phones. And some of these bits essentially gets flipped. So a simple picture like this is actually quite important. But you then ask, why do our mobile phones why don't it have jumbled messages all the time? So this is the world of information theory, where there are elegant results from channel coding. Basically, if we send more bits than we are to communicate, we can error correct with guarantees. And there is a trade-off. There's also a lower bound about how many extra bits we need to send in order to guarantee that the receiving end can actually recover the original coin flip, like the bit. depending on how much noise there is in the channel. So we can envision for the atmosphere, there are different levels of noise for different weather and different terrains in the city and urban areas, or outdoors in the open and so on. So that's that. So this whole part is worth about half, slightly less than half, 12% of your final mark, with the rest being accounted for in the programming part of assignment 1. Let me see. So for those of you who are new to Jupyter Notebook, just go to the directory where storage, type in Jupyter Notebook, and then click on the file, and then it will start essentially a Python instance that runs the notebook. I think probably because my machine is also recording, it's doing some work, it's taking some time to load the notebook. Okay. Right. So there are some do's and don'ts up front. So please read that carefully. So you are to essentially do your work in this notebook and submit it on Gradescope as right. And Gradescope will extract the parts of your work and auto-grade part of it and then manually grade, like we will, us and tutors will manually grade. So the part 1 is Bayesian linear regression. We are essentially working on a simple line fitting model. So the goal is to sort of work through some of the math. So and on Friday we're going to spend substantial time deriving this the expressions of the posterior of weights W, basically the expression regarding Mn and S sub of n. Okay, right, there are some pointers in the slides and in the book that will help you derive the identities. I believe this will ask you to derive the last step, not from end to end, which we'll do a walkthrough on Friday. And then when it says supporting code, it basically generates the data and does the plotting. So this is what we have provided for you. You should edit your solution. What you need to fill in is basically updates to the mean and variance here. And then given these data generation and plotting support code, the plotting support code is here, you should be able to generate the picture seen in the book. Let's see. A bit down here. Up. Okay. So your expected output should be like this, meaning given different amounts of data, what should the parameter posterior be, and also what the data, like the regression function look like. And the next part of the question, basically, you won't immediately get this figure 3.7 because the prior that's specified is a bit off, right? So you might ask, what if my prior knowledge is off, right? You will see an example of that. And then you can guess with a broader prior, and it asks you for what a better prior is. Should you shift it, or should you make it fatter or narrower or something, right? And then in part number 2, you're essentially using the same model but doing nonlinear fitting. You are using the Gaussian basis functions, just like the bias variance part of the lecture did. And then you are going to produce not exactly the same picture, but it will allow you to produce the predictive distribution picture. Then you can use your newly coded Bayesian linear regression on real-world data and observe results, right? The real-world data is what's called auto MPG dataset, basically miles per gallon in American units, or in here it's something like the inverse and scaled version of liters per 100 kilometers for different cars. And the features are number of cylinders, displacement, horsepower, and so on. Right. Again, there's lots of support code. So the goal is that you do not a lot of code, but you observe results. The section 2 of this particular assignment is the goal is to provide you a playground for neural networks and build intuition of neural networks. Those of you who have noticed that our team's logo is essentially a XOR function, right? A function like this, where, for example, there are 4 quadrants in the plane, and then the diagonally opposite quadrants have the same label. This is not possible to fit using a linear model without basis functions or linear basis function. So this question basically asks you to verify that you can't fit this function well using linear basis functions, and then you are to add sigmoid activation to these 2 neural networks, and then observe what the weights are so that you get a nearly perfect fit. Right, so that is that. So the call to right, so it also gives some directions to package your code for Grayscope. I think it is worth reminding people that Grayscope, the reason that we choose this platform is that we strongly believe this provides better feedbacks mechanism for both tutors and students, especially for students. So in order to submit the theory part, so if you log into Grayscope, you can see the 2 parts have separate entries, right? So for the in order to submit the theory part, okay, this particular assignment is not timed. Don't worry about it, and you can submit as many times as you want before the deadline. Right. So you essentially follow the directions in this submitting a PDF video. What you do is you upload your either handwritten but clearly captured PDF or typed. It's up to you. And then you will see the pages show up against the problem outline. Basically, we are going to grade it on the sub-question level. There are 17 of them. So you basically need to label which page each sub-question sits. So it's okay if one sub-question sits across 2 pages, then just select both of them. It's also okay if multiple sub-questions sits on the same page, then just select the same thing for the different sub-questions. And after that, the tutors will be able to essentially grade horizontally, like the same question for everybody, or vertically, like throughout for each student. So do that. And then the online assignment, there is also an instruction video here, so you can follow that. Moreover, there is a test, practice program assignment. This one basically asks you to check your Python version because Grayscope requires Python 3.6 or higher. And then it gives you a mini math exercise of F divergence. This one does not count towards your final grade, so you can either entertain yourself or just practice through the mechanism of doing Grayscope online submissions. Look at this release solution as well for your own amusement, right? So that's basically the assignment. I hope that helps. Is there any questions about the assignment or today's material?
Hi, could you explain a little more about when you try to analyze the variance versus the biases,
Right.
you said
You can
like
ask questions. So your tutorial time is essentially split between tutors will usually want to give you a rundown or walkthrough of the tutorial of that week. Um, um, and then they will also address any question you might have about the lecture and workshop material, which are highly overlapping, and also the assignment itself. Yes, you can ask tutors for help. They will not tell you how to solve it, but just yeah, they might inspire you with some ideas or tell you a few things to try or relevant sections of the book to look at. So one word about labs is that okay, we're in week 2 now. One word about labs is that they lag by 1 week to the main workshop and lecture material. And this week you will be looking at doing some linear algebra optimization and matrix decomposition in NumPy. What this helps is to get you used to the basic operations in NumPy, for example, matrix multiplication and how to implement things. And they are in general not exactly the same as the material covered in class. They are, strictly speaking, extension goals, right? Let me find. So, right, okay, this says dimensionality reduction, which I believe the previous week talks about PCA, and this one, in this one you will do singular value decomposition. So, which is the lecture talks about the ways to think about machine learning models, and then derivation of a particular type of class of models. And then in the tutorial, you will exercise your mind by essentially extend or use your learning to understand and implement and derive a related class of models, right? And this is how you build machine learning knowledge beyond this very introductory class. So in the neural network week, we're looking at classifications. We can click through and basically, so for example, in the lecture, we talk about kernel machines, SVMs mainly for classification. And here you're looking at kernel regressions. So that's that. The solutions to the tutorials are released at the end of each week. For example, there are both HTML versions and the notebook versions for you to run. The HTML versions were more for us to view. If you have done the lab for last week, you can see that there is, right, you're expected to do simple derivations for calculations on random variables. These are all markdown cells, and then you are expected to play with a toy data set and reading and writing CSV files. I hope that helps. That took quite a while. I'm going to stop the recording. I'm going to sit here for a few more minutes because this is my contact time weekly in case people want to hang out and ask other questions. Feel free to hang up or leave this meeting if you don't have other questions.